Now, we saw that when we squared a binomial, we got a trinomial. We got something with three terms. What if we just have a binomial where each term is squared? And notice that I have subtraction here. This subtraction is going to be important. But let's just start by completely naively trying to factor this using the AC method. The AC method is a method for trinomials, but we can always add 0 without changing anything. So let's see what happens if we add the term 0x. So we're trying to factor x squared plus 0x minus 9. So our AC is -9, our B is 0. So let's see, there are three ways we can multiply to get -9. We can take -1 times +9, -3 times +3, or -9 times +1. -1 plus 9 is 8, -3 plus 3 is 0, and -9 plus 1 is -8. Oh, okay. So I've got -3 and +3. I can split up my middle term as -3 plus 3. And then what happens? I can use the shortcut here, but I want to see the illustration. I've got my x squared and my -9. I've got my -3x and my +3x that I know add up to 0. First row, greatest common factor is an x. Then I need an x in the first column, a -3 in the second. I need a +3 in the second row, and +3 times -3 really is -9. We find that x squared minus 9 factors using just our regular methods as x minus 3 times x plus 3. And so what we notice is that these two factors are the same except the signs. And in fact, that will always work. If we have two terms that are perfect squares but they're subtracted, then we can factor that as two factors that are the same except for the signs. In more generality, if we have one binomial with subtraction, another binomial with the same two terms except addition, and we multiply that out, first terms will have a squared, outer terms will have plus a times b, inner terms will have minus a times b, last terms will have a negative b times b is b squared. Those two terms add up to 0, and we're left with a squared minus b squared. This is called a difference of squares for obvious reasons. We have two perfect squares, and we're doing subtraction to them. How do we recognize this? Well, first, each of our terms, if we ignore the signs, is a perfect square. And then second, the signs are opposite. One is positive and one is negative. So let's take a look at some examples where we can identify a difference of squares. In our first example, we have a 9x squared minus 16. So 9x squared, that's 3x all squared. Ignoring the sign for a minute, I have a 16, which is 4 squared. And then looking at the sign again, this is subtraction. So yes, this is a difference of squares. We have a squared minus b squared where a is 3x and b is 4. So 9x squared minus 16 factors as a minus b, so 3x minus 4, times a plus b, 3x plus 4. And since we did just write that down, we want to check. If we take 3x minus 4 times 3x plus 4, we'll get 3x times 3x is 9x squared. 3x times 4 is plus 12x. Negative 4 times 3x is negative 12x. And negative 4 times positive 4 is negative 16. Plus 12x minus 12x cancels out, and we get 9x squared minus 16, as we hoped we would. Okay, so that was a difference of squares. Here's another difference of squares. We've got x to the fourth times y squared as our first term. Now remember, when we square a monomial, we double every power. So half of 4 is 2, x squared. Half of 2 is 1, y. If we take x squared y and square it, we get x to the fourth y squared. And then we've got 36 z to the sixth. 36 is a perfect square. That's 6 squared. What number do we double to get the sixth power? Well, 3. 6z to the third, if we square it, we get 6 squared is 36. Z to the power 3 times 2 is 6. And finally, we see that this is subtraction, so this is a difference of squares. We'll have a squared minus b squared, where a is x squared y, and b is 6z to the third. So my x to the fourth y squared minus 36c to the sixth, that's going to factor as x squared y, that's my a, minus 6z to the third, that's my b, times x squared y, that's my a again, plus 6z to the third, that's my b. Now again, we just wrote that down, so we want to check. We're going to multiply x squared y minus 6z to the third times x squared y plus 6z to the third. So first terms, we'll have x squared y times another x squared y. Outer terms, we'll have x squared y times 6z to the third. Inner terms, we'll have negative 6z to the third times x squared y. And then last terms, we'll have negative 6z to the third times a positive 6z to the third. Okay, working that out, x squared y times another x squared y. Adding the exponents, we'll have x to the fourth y squared plus, let's see, multiplying these two, we'll have a 6, an x squared, a y, a z to the third. Multiplying the next two, we'll have a negative 6, an x squared, a y, a z to the third. And then multiplying the last two, we'll have a negative 36. And then z to the third times z to the third is z to the sixth. Again, those middle terms cancel out. And we're left with our original x to the fourth y squared minus 36 z to the sixth. Exactly as we hoped. Okay, So those two were differences of squares. Let's see some examples that are not quite. Z to the fourth, that's a perfect square. That's z squared squared. 81, that's a perfect square. That's 9 squared. Oh, but what's this operation? That's addition. That's not subtraction, so this is not a difference of squares. That's a sum of squares, but this is not the form we're looking for. Over here, y squared is a perfect square. That's just y squared. But x to the third is not a perfect square. So since the first term here is not a perfect square, this is also not a difference of squares. And that's all we can do with that. So these second two examples might look promising. It turns out they are not differences of squares.